for the recorder. Yeah.
Okay. The one for the room should not be so important because I speak loudly.
Yeah,
enough.
this is not a very big room.
So this should be good. I assume everybody can hear me at the back? Okay. Pass me the pen. We're supposed to get about 40 people in the class.
40 people, okay, so one.
By the end of the semester, there will be barely 15. So one of the problems of recording these things and broadcasting it is people pretend they're actually watching over Zoom. They don't really. And it gives them an excuse to not turn up. Nothing's showing. Slides.
Yeah, so just go to the other.
Yeah.
So if you go to.
Can you kill that turn up volume thing on top? And also.
So if you go to view, you just want to see the slide?
Yeah, yeah. Fold the paper like so. You fold it, in halves and the halves again inside. And so. Amit, you got to do better than that. I want something like this. And guys, don't forget to bring your name tag with you every time you come to class. Oh yes, thank you. And Adrian, can you have your name tag point that way so I don't have to come this way to find out who you are? Thank you. Fold it in 4 so you can make a little pyramid and then write your name on it.
So that mic is just for the people watching on Zoom. It won't be heard, won't be projected in the room.
So this is fine.
Just so the people on Zoom have clear audio.
This is good. This is good.
Yeah. The other mic is just will be heard in the room.
It's just that I want to confirm one time if the person in Zoom can actually see the slides.
They should be able to. If you're sharing on Zoom on here, they should be able to see the slides. Can you see how many people are on Zoom? Actually, if you go to. Okay, you can just send a chat and you're just sending a chat message and you're in here. Oh, do you want the one screen up?
That screen, please. Yeah, take a piece of paper, one of these sheets, and a pen, and make yourself a name tag. Fold it in halves and the halves again in half. All right, guys, slides up. Thank you. Okay, thank you, Paul. So, are we all set up? So, good afternoon, everybody. We are supposed to have 40 people in class. I don't see 40 people in class. I assume others will turn up. But welcome to this latest edition of Machine Learning for Signal Processing. I'm Diksha Raj. That's me. I'm the instructor. My TAs are sitting up front out here. This is Abhinav, Manohar, and Anish. You'll get used to them. I have another person, Alex Gichamba, is sitting over in Kigali. That's for the students in Kigali. So the course itself, before I begin, do you have any questions for me before I start? Anyone? No. So this is just the introductory lecture. Why is this not working? Huh. Great. Okay, got it. Let me jump right into the subject. The course is titled Machine Learning for Signal Processing. It has many little parts. It has machine learning, it has signals, and it has processing. So let's try to deconstruct a little bit. Folks coming in, just pick up a sheet of paper and write your name on it, right? Make name tags like this and take those bright pens. Now, let me ask some of you. Mayur, when I use the term signal, how do you interpret it? What according to you is a signal? Anything that conveys information. Do you guys all agree? Right. That is in fact very true. So a signal is a mechanism for conveying information. Gestures, traffic lights, semaphores. Do you know what a semaphore is? Anybody? What is a semaphore, Lucy? How many of you actually code? Okay, what's a semaphore?
It's kind of like a blue text, but with like multiple, I guess, like amounts of it. So it's a resource that you can like take and then.
A semaphore is a way of signaling. Guys, by the way, shut your laptops, please, all of you. So all of my classes are dumb classes. Your shared laptops and phones must be closed, except to answer polls, okay? So in the good old days, semaphores were just gestures. If you had like this guy over there with the two flags, this is how people would signal to trains or traffic which way to go. And so these were semaphores. Nowadays, when you're actually programming, semaphores are ways of conveying information from one module to another. So these are all signals. And electrical engineering, currents and voltages are signals. And in digital data, which is what we are going to be working with, signals are ordered collections of numbers that convey information, typically from a source to a destination. And sometimes the source and destination might just be yourself. For example, if you're storing something on disk, who are you conveying that information to? To yourself in the future, right? So those are signals too. And they're typically about a real world phenomenon. Let's look at some examples of signals, like an audio signal, a speech signal. If you look at it, it's just a collection of numbers. If you plotted an audio signal, it's going to look like the figure to the left. If you zoomed in, yeah, make yourself a name tag, please. Let me get you another sheet. If you zoomed in, you're just going to see a sequence of numbers, a time series. But the sequence of numbers represents a real world phenomenon. It represents a perceivable sound. Now, it's not a collection of numbers, it's ordered. If you change the order in which these numbers are presented, it's not going to represent the same thing. So also an image. An image is a rectangular arrangement of numbers or sets of numbers. And if you visualize an image, you're going to see something like this, but each pixel actually is just a visual representation of one of these numbers. If you're looking at a black and white image, the number would be binary, 0 or 1. If you're looking at grayscale images, it's going to be a value, continuous value between 0 and 1 or 0 and 255 if it's digitized. If you're looking at colored images, you're going to have 3 such numbers, 1 for each color. But eventually, it's just a rectangular arrangement of numbers. If you change the arrangement, it's going to represent an entirely different image. So the ordering is important, right? Or you can have other things. It may actually represent something in a transform domain. Everybody is familiar with what an MRI is. A magnetic resonance image is not just an ordered collection of numbers that represents the pictures that you see. This is a collection of numbers that are obtained in what is called a transform domain. We'll talk more about it later, from which these images can be derived. But that collection of numbers, ordered collection of numbers, is also a signal. Or other things like EEGs, ECGs, optical coherence tomography, right? Ultrasound, echocardiogram. All of these are signals, which in this case represent bodily readings. And financial data. These two are signals. These are just ordered arrangements of numbers which represent something that's happening in the market, like a stock price or like the value of an index. And they represent market trends. The techniques that we use for processing signals are often applied to financial data of this kind. And in fact, there are many special issues on signal processing methods in finance and electronic trading. most trading platforms, most trading companies do a lot of signal processing, except now the signals that they're dealing with are sequences of numbers that represent financial data. And many others, network data, weather, any stochastic time series can be a signal. In each case, the signal is an ordered arrangement of numbers that represents some real-world phenomenon. The key thing is that it's a collection of numbers. The numbers has an arrangement. If you change the arrangement, it's not going to represent the same thing. And typically, it represents some real-world phenomenon. So what is signal processing? It's what we do to obtain these numbers and what we do to these numbers. So there are different aspects to it: acquisition, like analysis, interpretation, and manipulation of signals, or where each of these again has many different aspects. Acquisition could include sampling, sensing. For analysis, you could be looking at decomposition, separating signals into their basic components. For manipulation, it could be denoising things, or it could be coding, you could be generating stuff. For interpretation, for example, in radars, sonars, and such like, you're taking decisions based on these signals. You can perform pattern matching, like in biometrics, prediction, for example, in financial data. Now, each of these are different ways of processing the collection of numbers to a specific outcome. So this is processing the signal. This procedure, this mechanism, this process is called signal processing. Now, I've categorized them into different categories, but the boundaries between these categories can often be fuzzy. And so when you look at a typical signal processing paradigm, there's a chain. You'd start off with some real-world phenomenon that's captured using some sensor. That sensor, so the numbers captured by that sensor is typically sent through some kind of a channel, and where you could be just sending the numbers as is, you could be coding it, you could be compressing it, you could just be storing it for the future. And then from these numbers, you're going to extract features, and then you would be performing some kind of analysis of these features. This combination of analysis, feature extraction and analysis, is what I'm referring to as pattern analysis in the yellow box. These are all different components of the signal processing chain. So much for signals and signal processing. The course is machine learning for signal processing. What is machine learning? Now, machine learning is, take a sheet of paper and write your name on it. There's a pen here. Okay, yeah, there's several of those. They're brightly colored pens. Okay, so machine learning is the science that deals with the development of algorithms that can learn from data. So here you're learning, you could learn the structure of data, such as in feature extraction, or learning patterns in data. If you're doing automatic text categorization, you're learning patterns in the text. You could be learning to classify between different kinds of data, different categories. Is this a flower or a cat? Or learning to predict data, like what is the market going to be like tomorrow? What is the weather going to be like tomorrow? Hi there, take some paper and write your names. You want sheet to enter, right? So the focus, given the other sheet, just fold it and write your name on it. Okay. So again, the focus here is learning, machine learning, machines learning to do things. And they're typically learning to perform all these operations from analysis of data. So when I'm speaking of machine learning for signal processing, we are combining these two. These two very disparate looking sciences, the science of signals and signal processing and the science of machine learning, and we're going to apply machine learning to every component of the signal processing chain. So you could be applying it for signal capture in sensing, such as in compressive sensing or dictionary-based representations, or for denoising signals using independent component analysis or filtering or some kind of separation technique. You can use this to determine or to come up with ways of passing the data that you captured through the channel, such as encoding or compression. Machine learning can also be used for feature extraction to reduce the dimensionality of data, or to learn about ways of characterizing the data. And then, of course, machine learning can be used for modeling and regression, like in classification or prediction, right? In every aspect of the signal processing chain, machine learning techniques can be used. So here's a poll. I typically have polls set up on Google Forms, but today I'm just going to ask you questions, ask you folks the answers directly. Can somebody tell me the answer to the first question? Let me pick somebody at random. Jimmy, what's the answer to the first question?
4.
4, right? How many blocks do we have in the complete signal processing chain? The way I represented it's 4, right? And yeah. Have a question? Okay. And Aisha, what's the answer to the second question? All of them, right? So the machine learning techniques can be applied to pretty much every aspect of the signal processing chain, from capture to the channel to feature extraction to modeling. So now machine learning for signal processing, the topic has 4 different distinct aspects. There's the aspect of representation. How best to represent signals for effective downstream or upstream processing. There are ways of doing it. Classically, we have deterministically defined methods for deriving these representations. In the machine learning world, we would learn how to derive these representations from analysis of data. For modeling, again, in the classical world, you'd have equations, you'd have physics, you'd have partial differential equations or ODEs, and they would be the models for your process. In the machine learning world, we're going to learn to model these processes through analysis of data. Classification, again, classification can be a rule-based process, but in the machine learning world, we are going to learn how to perform classification through analysis of data. And for prediction, again, how do you predict things from the future, things that you have not seen? We are going to learn how to do this by analyzing data. So machine learning for signal processing actually applies machine learning techniques for each of these 4 processes that are components of signal processing. So in this course, we're going to cover, it's a very big topic. What we are going to cover is a very small subset of the topics that we could possibly cover. We're going to learn about data-driven ways of deriving representations, algebraic methods for extracting information from signals. So we'll learn about deterministic representations which have no learning aspect to it. But then we're also going to learn about the learned mechanisms for deriving representations like principal component analysis, independent component analysis, non-negative matrix factorization, factor analysis, and linear Gaussian models. For representation and modeling, we're going to look at learning-based approaches for modeling data. We will learn about dictionary representations, about sparse and overcomplete characterizations. We're going to learn about regressions. You will not learn about neural networks. Now, this is the only class on campus where you will fail for using a neural network in any of your homeworks or assignments. If I see the term neural network in any report that you have written for me, I will give you a C instantly. So they are banned, right? Neural, and I can't even express the second word, it's that bad. So just keep that in mind. We're going to look at classical methods. We're going to learn about modeling, latent variable characterization, clustering, k-means, expectation maximization, and probabilistic latent component analysis. We will look at all of these. For predicting time series models, we're going to look at Markov models, hidden Markov models, linear and nonlinear dynamical systems, including Kalman filters and particle filters. We're going to look at classification and prediction, again, old classical methods, how you could perform binary classification and meta classifiers. Now, if I had infinite time, there are a whole bunch of other topics that I would have liked to cover, including privacy in signal processing. One of the biggest deals in today's world is how to keep data private while still getting information out of them, and how to keep the information derived from them private. So that's something that would be interesting to cover. Extreme value theory, also called black swan events. There are places in the world where it rains once in 100 years. But that one rain is extremely important. How do you predict it? There are very rare events that happen in the market. But those rare events are extremely important to know about. How do you predict those, right? This is extreme value theory. And if we had time, we'd go over extreme value theory. And we'd also try to look at aspects of dependence. How do you determine dependence of different aspects of the world, and how you can compute the significance of the results that you have obtained. But these remain a wish list unless I can magically manufacture some time. So the recommended background, if you know anything about digital signal processing, it's great. If you don't, you'll manage this course. You may have a little difficulty in understanding some topics, but overall you should be okay, although having a DSP background is definitely a significant plus. If you don't know linear algebra, you're in the wrong place because the course is entirely linear algebra. If you don't know your probability, you are probably in trouble. And since you don't know probability, you don't even know what I'm talking about at that point. But we're going to be looking at probabilities, not in great depth, but enough that it matters. And as far as the machine learning aspect of it is concerned, by the way, do you mind shutting your laptop? Sorry, laptops are shut in this class. Okay. So as far as machine learning aspects are concerned, if you have a background or if you've taken a course in machine learning, this is great. If you don't, we will probably cover most of what is required of you. So this website doesn't work yet. That's because I'm still arguing with CMU that it's okay for them to give me this website. In the meantime, the website that we have is this down here, cmumlsp.github.io/MLSP course. We will post this link on Piazza. Make sure to go on it, and all information relating to the course is going to be on this link. Now, with some luck, I managed to convince the powers that be that this is not a bad word, and that they can actually assign me this address. Okay. Now, logistics of the course. We're going to have mini quizzes every week. We have a whole bunch of them. We're going to pick the best 12 for you. And each quiz is going to be worth 2 points in the overall scheme of things. So they're worth 24 points. Quizzes will be released over weekends. I'm warning you in advance. I do not want to hear complaints about this. You have a fall break, but we are merciless. We're going to give you a quiz over the weekend of the fall break. Unless you want to have 2 quizzes during the week prior. That's your choice. I have a suspicion that you'd prefer the 1 quiz over the weekend or the break. So this will, because every week's quiz relates to the subjects covered that week. We will have assignments. We have 4 assignments. Now these assignments are interesting. They're not challenging if you know what to do. And if you don't, they can be very challenging. So how much time you spend on them can vary from 6 hours to 600, depending on how you go about it. So if everything goes right, it will not be a lot of work. There's a final project where we actually give you a bunch of problems to choose from. So the 3 problems that we have set up this time are, we are trying to do a self-driving car simulator, where you write code to control the car and avoid obstacles. We are going to do a little, what is that? Yeah, a karaoke machine where you replace a singer's voice with your own voice in a song. And the third one is predicting exchange rates. So the third project is where you have to predict exchange rates for different currencies, and you get to pick one of these. Yeah. You can, I'll just give you a C. Okay. So again, no neural networks, right? So again, I'm the instructor, and you can find me in 6705 Hillman Building. If you just walk along Forbes Avenue, and if you look towards Hillman Building, that blue patch represents Hillman Building. There are 3 floors, and the third window from the extreme left is mine. So if you ever wonder where to find me, just go up on Forbes Avenue, find that window, and find the room that's mine, and you'll find me. We have 3 TAs. Manohar, please stand up, and Anish, please stand up, and Abhinav, please stand up. All of them are students in the last edition of this course. We also have Alex over in Kigali right now. He has volunteered as of today, so I don't have his name on the slides yet. We'll add him. All the TAs will have office hours. We're going to post these on the course website. Please check the website. So, oh shoot, this website is, the link is wrong. We'll correct this. Lecture material will be posted on the day of each class on the website. And reading materials and pointers to additional information will be on the website. We're going to use Piazza. All of you must already be on Piazza. If you're not on Piazza, we'll add you today. Because we have the final roster for, almost final roster today, right? And so, any questions? Questions, anybody? None? All right. Also, please get used to me just walking up and down, because if I don't do it, now I am very aware, believe it or not, once upon a time I was a student, and I know that it was roughly at the 15-minute point that I fell soundly asleep, and there was nothing the instructor could do that could wake me up. So that hasn't changed. 15 minutes into the class, I will fall asleep if I stand in one spot. So my way of keeping myself awake is to keep walking up and down. So bear with me. The other thing is, I know you're going to fall asleep. So to keep you on your toes, you have these beautiful name tags, and I'll just randomly call upon you and ask questions. If I have no question, I'll ask you the answer to 2 times 2. But this makes sure that you're awake, right? So the story so far, we've looked at what's a signal, some types of signals, what is signal processing, what is machine learning, and where it applies in the signal processing chain. And for the rest of this lecture, today's lecture is very light. We're not jumping deep into any subject. We're going to talk about different kinds of signals and what we can do with signals and how. It's the notion of supervision. So we're going to look at principles of signal capture. We saw a signal is just a collection of numbers. What are those numbers and where do they come from? I'll explain them through examples of sounds and images because sounds and images are special. So the signals that you capture directly represent physical phenomena. The sequence of numbers that you get when you capture a sound represent the sound directly. The collection of numbers that you get when you capture an image represent the image directly. So you can, in fact, inspect the signals through using your eyes or listening to them. And so these are special. But then you have other kinds of data, like MRI data. The signal that you would capture has nothing to do with the final visualization that you see or any of the interpretation that you come up with. I don't even know how OCT signals are derived. Financial data, who knows what they mean, right? So there are different kinds of signals. We are going to look primarily at sounds and images in today's lecture, but I'll also look briefly at MRI to show you an example of a signal where the signal capture domain is very different from the domain in which you actually analyze it. For example, MRIs are visualized. The doctor looks at them, but what you capture is not the visual image that the doctor actually sees. So let's start with audio signals. What is an audio signal? Here's what a typical digital audio signal looks like. If you zoom in, it's just a collection of numbers, an ordered sequence, which I have plotted. The x-axis represents the index. The y-axis represents the value. Each dot, each asterisk represents one sample, one of these numbers. Now, what makes this sequence of numbers a sound? This sequence of numbers must represent a quantity that enables near perfect reconstruction of a sound stimulus. In the absence of this sequence of numbers has no relationship to sound. Now, so let's look at how sound is generated in the first place. How can you derive a collection of numbers of this kind that represents a sound? In order to understand this, we have to start at where sound comes from. Now, sound is just a pressure wave, alternating highs and lows of air pressure moving through the air. Now, can you hear that? Now, believe it or not, when I did this, I don't know if you can hear that, I moved air molecules. And these air molecules hit other air molecules, and those air molecules hit other air molecules. And eventually, a small number of these air molecules ended up in your ear and moved your eardrum. you actually heard the movement of air molecules, of pressure waves. That's what sound is. Now we are incredibly sensitive. I mean, the fact that I can do this and that you can hear it at the corner of the room tells you how sensitive we are, right? So when I speak, I'm producing pressure waves, puff after puff of air. And what you're hearing is the movement of air molecules when I generate these air puffs. Or if I pluck a string on a guitar, it's moving the air around the string, and you're hearing the movement of this air. Now, how do you hear this sound? This movement of air creates highs and lows in air pressure, which radiate around the room, and eventually they end up in your ear, and they move your eardrum. The highs in air pressure will move your eardrum in, the lows will suck it out, and you're going to sense the movement of your eardrum. Exactly how do you sense this? I have a picture of what your ear looks like. That's your ear. You have this long tube over here, which is the external auditory canal. At the end of the canal, you have the eardrum, which is a membrane that is moved by the air pressure. And then the movement of this eardrum is transmitted through 3 bones into the movement of fluid in something called the cochlea that you have in the ear. Now, instead of me trying to explain this, let me use a professional. This is from Siemens. Why is there no sound? Can you hear sound? Okay, so wait a minute. Can we increase the volume? Can you check the volume over here? Video. Yeah, that's it. Is that it? This is crazy. Now, give me a second, guys. There is a sound going out of, yeah, HD audio driver, right? It's going through this. And so these magical things will happen initially. This one, let me see if I can share the sound. It is.
Okay, can you go here?
Wait a second. Let me stop sharing. Give me a second, guys.
Go to the area. That.
Wait a second. And how do I go up to this control? It is.
If you want to share screen, just click the green one. This one, not that.
Yeah, but then it will ask about sharing sound.
Sound is connected. Just computer audio. No? Yeah, it's correct.
Okay. And I'm not sure if this will actually work. Let me try. No. I need the sound. Okay. Okay. Okay, perfect. All right. All right, Ken.
The world is full of infinite sounds, but how do we actually perceive them? Sounds are collected by the outer ear, which consists of the auricle and the external auditory canal. The sound is guided through the ear canal to the middle ear. The sound arrives at the eardrum, a flexible circular membrane, which
It's very dramatic. I've got to figure out how this happens every semester. So in the typical semester, we spend the first 15 minutes dealing with Zoom. But you get the idea, right? So here's what happens. Sound is a pressure wave, and it moves your eardrum, and the movement of the eardrum sort of travels, it's transmitted through a series of 3 bones into something called the cochlea, which looks like this. It's a circular canal in which there is fluid, and there's fluid which goes up the top and comes down the bottom, and between the two are 2 membranes, and between the membranes are hair cells. The hair cells are different lengths and connected to different portions of the cochlea, and each hair cell acts like a tuning fork. And so depending on the movement and the frequency with which the fluid moves, the different tuning forks vibrate, and what you sense as sound is simply the movement of the tuning forks, which are the hair cells in your ear. Now, all that is fine. The key point is that the way we sense sound is through the movement of the eardrum, because it's a pressure wave. So if you want to capture sound, and if you want to capture numbers that represent or that characterize the physical phenomenon through which we ourselves perceive sound, we want to do that by sensing the movement of the pressure waves. And so we start off by your typical microphone comprises a diaphragm of some kind, and the diaphragm is highly sensitive, and the movement of pressure, the movement of the pressure waves moves the diaphragm. Now the motion of this diaphragm is converted through some mechanism into an electrical signal. So for example, the diaphragm could be the front of a little cell which has carbon granules in it, and when the diaphragm moves, the carbon granules get compressed or rarefied, so the resistance of this device changes. If I simply applied a voltage across this device, the current that goes through it is going to change with the movement of the diaphragm. And so you're going to end up with a continuous electrical signal of this kind, of the kind shown over here, which shows you how the diaphragm has moved. And to convert this to a sequence of numbers, we're going to take snapshots of this movement at uniform intervals of time. And those snapshots are the sequence of numbers that eventually become the audio signal that you have stored on the computer. So now eventually you're going to end up with just a collection of numbers of this kind. How do I know that this arrangement of numbers represents a real sound? Now the only way I know that, if I were to ask you, how do I know that this collection of numbers represents a sound? So Johnny, what would your answer be? How would you play it? Anybody?
Sending audio signals to a speaker so that it drives the coil.
These are just a collection of numbers. So how do you see? Anybody else? Akanksha? Yes. Yes, Lucy?
Would the numbers represent the frequency or how strong?
Are these numbers representing frequencies? Isabel, do you have an answer?
I thought so.
Jimmy?
They're like speech samples, but
These are speech samples. So here's what you would do, right? You know that this collection of numbers is supposed to represent the sound. This collection of numbers has been obtained by taking readings at uniform intervals from the original electrical signal. So what I would do on the receiving end is to have some kind of a circuitry which connects these numbers up into a continuous signal of this kind. And this continuous signal is now going to move a membrane. That's what your loudspeaker is. Now this could be, for example, through an electromagnetic coil where the magnetic field itself is changed. I could have a little metal strip on the diaphragm. It moves the diaphragm back and forth. And if all goes right, the movement of the diaphragm over here is going to result in a pressure wave almost identical to the pressure wave that moved the diaphragm in the microphone in the first place. And so you would reproduce the sound. So that's how you would actually, that's how you know that the sequence of numbers represents a sound. So when I think of it, how do I move this darn thing on top out now? This is. Okay, thank you. Right? So once I know this, I have a question, right? How frequently do I, oh God. How frequently do I take these readings from this electrical signal in order to ensure that the sequence of numbers I get represents a sound? Yes. It paused the recording? Oh, good God. Can somebody help me with this? I'm sorry, guys, we've got to get this sorted out. Okay. So I still want to hide the floating controls. Okay, right. Okay, right. So now this is extremely annoying because once I do this, I cannot. Let's see. I don't know if the recording is continuing or not. We'll deal with it, right? So now the way we converted this sound wave to a sequence of numbers is by taking readings at uniform intervals of time from this continuous electrical signal. Now, how frequently do I need to take these readings in order to be sure that this represents a real signal, the signal that I actually captured? In order to get an idea of this, it's convenient to think of sounds in terms of frequencies. Why frequencies? Frequencies are the most natural way of thinking of sound. Our ear, as I told you, is just a collection of tuning forks. And what we sense as sound is simply the resonances of these tuning forks. And what do tuning forks respond to? Frequencies. So it makes sense to think of sound in terms of frequencies. And so any sound can be modeled as the sum of many sinusoids of different frequencies. And again, as I mentioned, the frequency is a physically motivated unit. So how many frequencies? I don't know if you can hear this. I'm going to try. Okay, I'm going to play some nasty sound with echoes, and I want you to tell me how many frequency bands you can hear. So it's capturing it from the. No, I can mute this.
Is it muted from here as
Yeah.
You might have to reduce the volume if you don't want the echo to come. So once you play it, then just reduce the volume.
Okay. Let's see if this works. It doesn't. Let's leave it. I'm going to have to get Paul to fix this next class, but this is not working. So we can hear sounds all the way up to about 20 kilohertz nominally. The reality of this is that a newborn baby can hear 20 kilohertz. As you grow older, all of those hair cells in your ear, they begin breaking up. It starts off with the hair cells that represent the highest frequencies because they're the longest hair cells. And so by the time you get halfway through your life, a good number of them are gone. By the time you get to my age, many of them are gone. I can barely hear 12,000 hertz. These girls here can hear all the way to 16,000. Some of you can probably hear all the way up to 18,000, and newborns can hear up to 20,000 hertz. So the point is, sound itself has many different frequencies, and I have a problem. I have more audio examples, but anyway, I'll skip those. So when we sample this audio signal, we are sampling this continuous signal, and we want to make sure that the rate at which we sample it, something that we call the sampling frequency, is sufficient for us to recreate the original stimulus completely. So sampling rate is measured, the sampling rate is measured in hertz, samples per second. And since we can hear up to 20,000 hertz, we want to sample at twice the highest frequency that you want to capture in the signal. Now, for this, to give you an idea of how this works, look at the sinusoid. If I take samples very frequently, like I show in the first picture, if I simply connect all these dots up, it's going to give you back something that looks like the original sinusoid. On the other hand, if I take a sample only once per cycle, then if I simply connect the samples up, what originally started as a sinusoid, when reconstructed simply gives you a constant line. So you've lost the signal completely. And if I take a sample too infrequently, like in the third picture, if I connect these up, then as you can see, the connected up recreated signal has nothing to do with the original frequency. It's much lower than the original frequency. So for you to be able to reconstruct the signal completely, you need to be able to take at least 2 samples for every cycle of the original signal, which means that the sampling frequency has to be at least twice the highest frequency that you want to represent. So how does that work? I have lots of audio signals, which I'm not going to play because we know that it's unpleasant. But then, actually, let me do this to you anyway. Right? This first signal here is a frequency sweep going from 0 to 20 kilohertz. And I've sampled it at 44,100 samples per second, which is higher, more than twice the highest frequency being 20,000 hertz. And so I'm able to reconstruct all of it. But if I were to sample the same thing at 22,000 samples per second, the highest frequency I can represent is 11,000 hertz. Anything above 11,000 hertz is going to get reconstructed badly, like in the third figure. And so the frequency that you reconstruct is going to be very different. So this picture here is a spectrogram. The x-axis is time, the y-axis is frequency, and the color represents the energy in each frequency at each time. So the first picture shows you that it's a sweep going from 0 to 20 kilohertz. Now in the second picture is the signal that was reconstructed when I sampled the first signal at only 22,000 samples per second. And when you do that, here's what the reconstructed signal looks like, sounds like. That's this guy here. You can see that anything over 11,000 hertz, when it's reconstructed, doesn't sound like the original frequency. It sounds as something lower. It gets reflected down, right? What happens if I sample at 11,000 samples per second? Here, the highest frequency I can represent is 5,500 hertz. And so, anything over 5,000 hertz, 500 hertz, gets reconstructed as something below 5,500 hertz. And the higher the frequency gets, the lower the reconstructed frequency, until you get to 0 hertz, and then it begins to go up again. And so the reconstructed frequencies bounce between 0 and 5,500 hertz, although the original signal went all the way from 0 to 20,000 hertz. And this is simply because you sampled the signal, you did not sample the signal frequently enough, you sampled the signal too infrequently. Now, it's not just in sound, this also happens in images. So here's a nice little grid pattern. The figure to the left samples these frequencies at a certain number of pixels per inch, and the figure to the right samples it at a higher number of pixels per inch. And you can see how in the figure to the left, as you go to the back, as the frequency of the image increases, what is reconstructed is utter rubbish. Whereas in the second picture, you can actually see that because this has a sufficiently high sampling rate, you have to go all the way up here before things begin to get distorted. So you're able to reconstruct frequencies that are up to half the sampling frequency of the image. Now, and this is also true for video, right? This is this famous video that everybody has seen. That's a propeller. What's happening here? Anybody? Yeah. So the frames per second is perfectly synchronized with the propeller. So every time it captures the propeller, it's in the same position. Does that mean the propeller isn't rotating? It's rotating incredibly fast, right? It's just that your capture rate is so slow that what it's reconstructing is completely wrong. And this is what you're going to see. So in order to be able to represent the signal properly, you really need to sample it at least twice the highest frequency. And capture at the wrong rate can give you an entirely wrong idea of the signal. I have some real audio signals, but I'm not going to play them here. Right. Now, there are a couple of different things that can happen here. First, I'm not sure why that propeller is continuing to rotate. Where is it? Where is it? Do you hear the sound at the back? We need a different room. Okay. So here's what happens. If I sample too infrequently, we were unable to represent the signal properly. But not only were we unable to represent the signal properly, when we reconstructed it, it came out all wrong. So the original signal, for example, over here, went from 0 to 20 kilohertz. When I sampled it at only 22,000 samples per second, it was only able to represent frequencies up to 11,000 hertz. Anything above 11,000 hertz got distorted. It came back as a lower frequency. Now, the question is, do I really want this to happen? I know I'm going to lose this, but do I want it to come back as a ghost? I don't. And so in your standard sampling paradigm, signal capture paradigm, you have something called an anti-aliasing filter. An anti-aliasing filter is going to actually cut off all the frequencies that would get misrepresented at the current sampling frequency, so that although you may have lost them, these frequencies don't come back as rubbish that's going to destroy your signal. So in this case, when you actually use an anti-aliasing filter of the right kind, if I sample this too infrequently, the signal that you reconstruct will have frequencies up to 11,000 hertz, and then everything above 11,000 hertz is going to be lost. But this is better than having those things come back and destroy your original data. So also, if I was sampling at 11,000 hertz, the highest frequency I can represent is 5,500 hertz. So your anti-aliasing filter is going to delete everything above 5,500 hertz. And so when you reconstruct the signal, you're only going to get stuff up to 5,500 hertz, and the rest of it is gone. This is still superior to having those things come back and appear as something completely wrong. Now, there's another aspect to capturing sound, yes.
Isn't the video like the propeller one? Isn't it like correctly reconstructed? It's correctly reconstructed, right? But they have exact number of samples, like per number of frames per second.
In terms of the video, is it representing the original phenomenon?
There's no original video like the ground truth.
What is the ground truth for a video? What do you think it is? Do you think the propeller is just stationary?
No, it's moving, but
Exactly.
with low number of frames, it would seem like it's like moving, but with like high number of frames per second, it will be stationary, right?
With high number of frames per second, you would actually capture it moving. If I took only one snapshot every second, would you see movement?
Okay.
Right. So you need to sample it frequently enough, yes.
For the video, you say it's aliasing, right? But we have this with an filter before the sampling.
So the notion of,
Video will look like.
so again, over here, what is the notion of an anti-aliasing filter is very unclear for video because you're speaking of motion. For sounds and static images, it's a different thing.
Yes.
So I don't, again, it's more complex. I'm not really sure what it would look like. I haven't thought about it. Let me answer later, right? So anyway, there's a second aspect to it. Sound is a continuous signal. But numbers that you store on the computer are not continuous. They're all integers, right? You have a fixed resolution in bits. And so because numbers can only be stored to a finite resolution, you're going to have differences in how you store, you're going to have artifacts from how you store the numbers. For example, if you're representing every sample as a 16-bit integer, you can store a maximum of 65536 values. But the sound itself is continuous. It can take any arbitrary value, right? And so this low resolution of storage results in loss of information. For example, if this figure in the top is the actual signal that you're trying to capture, store, but if you store this using, say, only 8 bits per number, that means there are only 256 unique values that you can store. So the value that you're storing on the computer is going to be the second figure. And as you can see, it begins to look like a little staircase. If I store this using only 3 bits, this guy ends up being stored like this. If I store it using only 2 bits, it looks like this. For 1 bit, it only looks like this, right? So this obviously is going to cause a lot of degradation in the signal. So here, for example, now let me try this. Pardon me, folks, for whatever I inflict on you. So this is Tom Sullivan, Professor Tom Sullivan of ECE. Can you hear him? Okay.
SULLIVAN.
But if I store these using only, that's stored using 16 bits per sample. If I store these using only 5 bits, here's what it comes out as.
SULLIVAN.
Slightly noisy.
SULLIVAN. SULLIVAN.
Now here's the amazing bit. If I store this using only 1 bit per sample, this is the signal that you're storing. Can you see anything useful here? Let me play it out.
SULLIVAN.
So the amazing thing is that our ears are extremely forgiving, and they do a lot of processing. Something that looks like junk still comes out as something that you can actually perceive. That's because this is speech. If I were to do the same thing with music, which I won't try to play because it'll kill your ear, especially with these acoustics, it's, as you decrease the resolution, it's going to sound more and more crappy. Eventually, it's going to sound like pure rubbish. So, which is why we like to. So, the two things the two take-home lessons here are: first, you want to capture the samples with sufficient frequency. 3 take-home lessons, right? You want to capture the samples with sufficient frequency so that all the frequencies you're interested in are stored. Second, you want to filter out the frequencies that you're not going to be able to represent before you do the capture, because otherwise they come back as ghosts and they're going to make things ugly. And 3, you really want to capture these samples with sufficient precision, a sufficient number of bits per sample, so that they are stored with high fidelity. Now, for typical speech, we capture speech at 16,000 samples per second. We use 16 bits per sample, and we're able to hear this just fine. But in music, for example, they usually capture these things at 96,000 samples per second to make sure that even the highest frequencies are well captured. And then they capture this at 24 bits per sample to make sure that the individual samples have very little distortion, if at all, right? So these things matter. Now, here is my second quiz. Anybody want to answer this question? Prem, want to answer this question? Yes?
It's possible to recreate the original sound.
Absolutely, right? The only true test to verify that you have digitally captured a sound perfectly is if it is possible to recreate the original sound perfectly from the digitally captured signal. There is no other test that is perfect. Yes?
Go back a few slides earlier to the anti-aliasing slide.
Which one?
The anti-aliasing. Yeah, this one. So if you're doing the anti-aliasing filter, why is the recreated sound file shorter?
The recreated sound file is the full length.
But
It's just that the vertical axis, this went to 22,000. This is going to just 11,000. So,
silent after the mid.
yeah, that's because these things, so if the vertical axis were the same scale, so this would just go to the halfway point and disappear, because the sampling frequency is such that it cannot represent anything above 11,000 hertz. So we've deleted it. So at the higher frequencies, there are no other there's no signal. In this case, I have a sweep. As time progresses, the frequencies are increasing, which is why time is the same as frequency over here, right? The second half is gone. That's how. Okay, let's look at the other kind of signal, images, right? How do we see images? We perceive images through our eye. And as it turns out, our eye is just a very glorified camera. So how exactly do we sense images? That's what your eye looks like. You have an eye, you have a lens over here, and the cornea, of course, protects the lens. The images come in, they get reflected by the lens, and they are eventually projected on the retina at the back of the eye. The retina senses light. So how does the retina work? Here's how it works. I've always claimed that the retina is a perfect example of unintelligent design. So, and why so? Here's what the retina looks like. The retina consists of sensors. There are two kinds of sensors, sensors that sense light intensity and sensors that sense color. These are the so-called rods and cones. Now, in the human, the only animal on earth that I'm aware of that has a properly designed eye is the octopus, because you have the sensors outside the nerves. In the case of the human eye, it's an extremely crappy design. This is how light comes in. It comes in from the back. It passes through a sheath of nerves and has to go past all of these nerves until it eventually hits the sensors. So the way it is set, the sensors feed signals to the nerves, and the nerves fold back and go through a hole in your retina back to the brain, which is why all of us have a blind spot. Because in that spot, there are no sensors. That's where the nerves are folding back and going back into the brain, which is a very stupid design. I, as an engineer, would never design a camera like this, right? Now, secondly, this has a second issue that as we grow old, we grow blind, not because we've lost sensors, but because this sheath of nerves gets damaged by macular degeneration. So there are many reasons to believe this was some kind of evolutionary artifact with things that shouldn't really be. But anyways, so here's the point. The actual sensors are these two kinds of cells, the rods and the cones. The rods sense light intensity. They sense the presence of light, but they don't sense color. The cones sense color. And so the rods are fast, sensitive. They basically generate grayscale images, and they dominate in the periphery of your peripheral vision. The cones sense color. They are slow to respond. They're not very sensitive, and they're predominant near the center of your eye, in your fovea, or what's called the macula. And in fact, when you look at me, you're sensing color. You think you're seeing color all around, but you really don't. You're only seeing color in the very center of your vision. Everything in the periphery, in your peripheral vision, is black and white or grayscale. You imagine color in the gray, out to the corners. You're filling stuff in. Your brain is lying to you every second of every day, every time you look at an image. And so this is basically what happens. Now, the density of the cones is highest at the fovea, the region which is this region. This is where the nerves foolishly fold back and go back into your brain. And so that's your blind spot right there. You have this spot in the middle where you have the greatest density of cones. That's where you sense most of your color from, which is why you have to look at something to understand its color decomposition properly. And the periphery is mostly black and white. Now this fovea itself, there are different structures. Eagles have two fovea, which is why they can see a little worm on the ground from 1 kilometer high up in the sky. And animals like dogs and cats don't have a fovea. They have a long foveal slit with lots of sensors, which is why their night vision is so good. Now, the way we sense light is that we have 3 types of cones. And the 3 types of cones have this kind of response to different wavelengths. The x-axis is wavelength. The y-axis is the sensitivity. And so we call them the blue, green, and red sensors. So the blue cones have this kind of response where they respond most to light with wavelengths between 400 and 450 nanometers. Now the green cones have this sensitivity, this response shown by the green curve, and the red cones have the response shown by the red curve. And now the exact nature of these responses differs from person to person. And so in fact, very often these two things can be so close that you get a, what do you end up with? Color blindness, right? Because you can't distinguish between red and green. Now, anytime you look at traffic lights, the first thought that comes to mind is how stupid. Why? Because we are most likely to confuse red and green. Blue is way out, right? And so Now again, the so-called blue sensor responds to all wavelengths. It's just that it responds most to wavelengths in the 400 to 450. The so-called green sensor responds to all wavelengths. It just responds most to wavelengths in the 500 to 550 range. And the red sensor responds to for the 550 to 600 range, more or less, right? So when, so the so-called blue light sensors respond to all wavelengths, and the difference in response of green and red is small, varies from person to person, which means that each of us really does see the world differently. You must often have wondered, every one of us has no doubt wondered, is my red the same as your red? Is my yellow the same as your yellow? The answer is no, it is not, right? No two of us see the same world. The world is entirely different. We just sort of agree upon a common language, and we sort of kind of get along. So now, what about white light? How do the sensors in our eye respond to white light? It happens that the area under each of these three responses is the same. And so if I have light with a particular collection of wavelengths, then the way the blue sensor responds, the response is the integral of the area under the curve within the range of wavelengths that is actually presented to us. So when I have white light presented, the area under the curve, which is the product of the original spectrum and the response, the integral of the product of the curve and the response is going to be the same for all three kinds of sensors. So when you have white light is a light which has all wavelengths to equal amplitude. And so the red, green, and blue sensors all respond exactly alike. Conversely, our brain says, anytime my red, green, and blue sensors have exactly the same response, this light is white. But is white light the only thing that generates this kind of response? What do you think? Black, here's another example, right? Look at the guy at the bottom. It has three wavelengths. Now, if I take the response of the blue sensor, the response of the blue sensor is obtained by multiplying this curve by this spectrum and taking the integral. So also for the green and so also for the red. And guess what? This light at the bottom is also going to elicit exactly the same response from all three sensors. And we are going to think it's white. But is it white? Would this light be white? Anybody? Can I hear a yes? Or can I hear a no? Okay, I want everybody to say yes or no. It's not white. It has only three wavelengths. White light has all wavelengths to uniform amplitude, right? So here is this light which has only three wavelengths, but you sense it as white. And so this is where our digital camera begins to differ from the real world. Many combinations of wavelength can produce the same perception of color. So when I sense a yellow, there are millions of combinations of wavelengths that can generate the same sensation of yellow in my eye. But would it generate the same sensation of yellow in your eye? Yes or no? No, because why? Because each of us has different responses. Our cones have different responses, right? So if you designated a specific wavelength as yellow, then yes, all of us would see that yellow is more or less the same. But there are different combinations of wavelengths which all of us would perceive as yellow, and we are all going to perceive those things very differently. So not only do we see the real world differently, we see the digital world very, very differently. No two of us are seeing the same thing, right? And then there are we have other cases like tetrachromatic animals. This estrildid finches and goldfish have sensors with four different kinds of cones with these responses. Now, the way they see the world is entirely different from the way we see the world. So when I see a TV, for instance, the way we do it, our TV actually has only three wavelengths, red, green, and blue. And we sense colors. We kind of agree that this is yellow, this is the color of skin, this is black. These poor animals, if they saw our TV, they'd be very, very confused because it doesn't look anything like what they're used to. So how does the digital camera work now? the digital camera tries to emulate the eye, but it's a kind of a crappy emulator for the eye. You have a lens, the lens projects images on a sensor, and the sensor comprises sense elements of 3 different wavelengths, one representing red, one representing green, and one representing blue. And what we do is to try to emulate the response to every single wavelength that can be incident on our eye through different combinations of these 3 wavelengths, in much the same manner that both of these guys generate the same response. I could have a particular color which is 600 nanometers in wavelength, and I could try to generate the same response by some other combination of wavelengths. And the specific combination of wavelengths that we choose are the wavelengths that we've designated as red, green, and blue, each of which has a specific wavelength. And you have a large number of these sensitive elements, typically 200 to 600 pixels per square inch. And there's also usually an anti-aliasing filter to eliminate this high frequencies to make sure that this density of sensors doesn't result in distortion due to aliasing. So not only are you restricting the colors that are actually being captured, you're also restricting the frequencies that are captured in the image. So your digital image is a lie. It's a lie in many different ways. And we utilize the trichromatic nature of human vision to trigger the 3 cone types to produce a sensation approximating the desired color. And the 3 chosen colors are red, green, and blue, which have 650, 510, and 475 nanometers. And this can still represent only a tiny fraction of the 10 million colors that the human eye can sense. So in fact, the most modern cameras have begun using a larger number of, there are 2 aspects to it. There's the digital capture. The camera captures only 3 wavelengths, and then your computer screen only displays 3 wavelengths. And by manipulating these 3 wavelengths, we fool our eyes, our brain, into thinking there are many colors. So the more of these wavelengths you can sense and the more of these wavelengths you can emit, the better a job you're going to be able to do of fooling the eye, fooling the brain. And so modern satellite cameras typically use 7 wavelengths. They capture 7 colors. And so if you look at satellite imagery on a proper screen which is capable of generating 7 wavelengths, and you look at an image that was actually captured using a camera that captures 7 different wavelengths, you're going to see a massive difference in the quality of the image that you see compared to what you see with a standard camera and a standard screen. So, and in order to get better and better quality representation of images, the number of wavelengths, one way is to simply have more pixels per square inch, but that doesn't cut it. So the other dimension along which these things improve is by increasing the number of wavelengths that you can capture in your camera. This comes with other challenges. We won't get into it, right? So when you look at computer images, when you're looking at a grayscale image, you're basically just storing one value where the R, G, and B values are the same. And you're going to see an image of this kind. But if you zoom in, each pixel is going to be just one number, which represents a single value that's applied uniformly to R, red, green, and blue. And within the computer's own brain, what the computer really sees is not this image. The computer sees a function, something that changes with position, a specific value. Whereas if you are looking at a colored image, each pixel is actually going to have 3 different emitters, one emitting red, one emitting green, and one emitting blue. So when the camera captures an image, it's actually capturing 3 images. It's capturing an R image, a G image, and a B image. And you're seeing all of them together. So anybody want to answer this question? Let me pick somebody randomly. So, Isaiah.
There's infinite number that can create the impression of light to the human eye.
Perfect, right? There are infinite combinations of wavelengths that can all result in an impression of white in the human brain. There's a very standard definition of white, all wavelengths to the same intensity. But the sensation that we would get when we saw an actual white light can also be emulated by many different combinations of wavelengths. So again, you have quantization effects. Captured images are typically quantized to 8 bits, which is only what, 255 to 1, right? That's the ratio. But the human eye can sense distinctions of 5 orders of magnitude, 10,000 to 1. And in fact, most cameras only, although they may have 8 bits per color, the actual resolution is only 6 bits. So they're going to give you 1 to 64, whereas the human eye can go from 1 to 100,000. So while we can see 10 raised to 15 different intensities of light and combinations of light and color, your camera is going to give you 64 cubed. How much is that? A few thousand. So again, not only is the camera showing you the colors all wrong, not only is it cutting out high frequencies, it's also giving you a very wrong notion of the intensity of the light, which is why a digital image can never really be real life. Right? So when you process images, typically we work on grayscale images, you just average RGB for classical algorithms, but you can work on RGB separately. Anyway, let me move on, right? Questions? None. I'm going to go a few minutes over, guys, because we've been messing around with the screen. So speech and images are just examples of signal where the digital image is a facsimile of the stimulus to be represented. But then, there are other kinds of signals of this kind, like biosignals, network traffic, and so on. But here's a signal where the digitized signal is not a direct facsimile of the image to be represented. The signal is captured in the transform domain. Now, all of you are familiar with MRIs, right? Who has not heard of an MRI? Nobody. No. What is an MRI? It captures the interior structure of soft tissue. How do you take a picture of the interior of soft tissue? Any ideas? How do you get a cross-section of the human body? How would you do it? Yeah? So here's how it does it. You create a magnetic field of a specific frequency with a specific wavelength. And when I create a magnetic field of that specific wavelength between the front and the back, the cross-section of the human body has many different sections of different dimensions. So these space lengths change, and the portions of the body whose spacing matches the wavelength of that particular magnetic field begin to resonate. And so you can capture the energy, the total energy of all the components that have that particular spacing. Then you sweep through the frequencies, and you capture this image at every possible frequency, all possible wavelengths. And this basically gives you what component of this cross-section has spacings of different kinds, the Fourier transform of the cross-section of the body. And then once you do that, and you do this in all 3 dimensions, then you have to perform an inverse Fourier transform to actually generate this image. So the image is not actually slicing the human body, thankfully. It's doing so by just computing, actually capturing the image in the transform domain from which the data are recovered. So now you get an idea of what the signal can be. The signal is not a direct facsimile of what you're trying to capture. It's something else from which this can be derived. So the image changes left to right, top to bottom at different rates at different locations with different tissue densities, which show up as spatial frequencies. So we take slice-wise measurements in the Fourier domain. You have a single gradient field which derives response at a single frequency, spatial frequency, which can be measured. You go through a sequence of gradient fields which derive resonant response at different spatial frequencies in the tissue slice. And then this gives us a 2-dimensional Fourier transform at each location. We do this at several locations. We perform the inverse Fourier transform to actually generate the image. Very impressive technology if you think about it, and the fact that we managed to pull it off. So what is the key difference between MRI imaging and an X-ray? Anybody? Abhishek?
Sorry, sir. X-rays are just 2D.
Can pass through flesh but not bone.
I have choices here. One of these 4 choices. Tell me which of these holds. Number 3? Right. MRIs are captured in the transform domain and must be decoded to get the image, whereas X-rays are directly captured in the image domain, just through reflections, right, and absorption. So that's the key difference. why MRIs are so much more expensive and yet at the same time so much more informative. Now, I'm going to spend like 5 minutes on going through machine learning challenges of dealing with data. The kinds of things we want to do, we want to have signals can be decomposed into combinations of building blocks. You have all of these different signals. And different signals of any category can be thought of as different combinations of the same building blocks. Even in the case of signals, you can think of what composes these signals as a collection of Lego blocks. And by putting the same set of Lego blocks together in different ways, you can construct different objects. And so the idea of deriving representations and decompositions is to figure out what the Lego blocks are from the signal so that you can put these back together to reconstruct the signal. Now that's all very fine in words. Mathematically, what is this? If I have a signal S, then I can think of the building blocks as some variable B, and the manner in which I compose these building blocks together as some variable W, and I want to find B and W through analyzing S. And there are different ways of doing this. How we do this is the representation problem. Now, what is this thing on top? This is so annoying. Let me see if I can hide this or. So what about modeling? Signals are produced by processes, which are generally partially or fully unknown. And somehow we must interpret and learn about this process in order to process and analyze the signal. So the knowledge of the process is crucial for additional processing. And the machine learning challenge here is characterizing the process underlying the signal through statistical properties of the signal or through an abstract parametric model. Now, the other challenge is classification, right? Signals may arise from different classes of stimuli or processes. And we often need to identify the underlying process or the underlying stimulus. The machine learning challenge over here is to identify the underlying class of the signal. I mean, for example, is this guy over here a sink or a face, right? I mean, depending on how you look at it, you end up with different answers. Now, prediction. Signals can be analyzed to make predictions into the future, about the future of the signal or the underlying process. And the machine learning challenge over here is how do you actually make the best predictions? There's the notion of supervision. Learning representations and modeling the data are preliminary steps to other processes like classification and prediction. So this can be performed either with or without reference to the actual task it must perform. So this, when you do not have an explicit reference for what you're trying to do, you end up with unsupervised learning, which can be explicitly optimized. But if you have a reference saying this is an image of a face, then you have the notion of supervision. And so in this case, whatever you learn is going to be derived on the basis of the supervision. I'll stop right here. The primary tools of the trade that we're going to be using are linear algebra, some calculus, optimization, and probability. Again, we're not going to be using neural networks. So I will continue in the next class where we get serious. All the fun stuff is over. From now on, it's only pain. And we'll be talking about algebra. Thank you.